Welcome back to the deep dive. Today we're doing something a little different. Usually, we take a topic and we look at the headlines, the flashy stuff. But today we are going back to the source code.
Literally the source code.
Literally, we're talking about the blueprint of life itself,
The
DNA.
It's the foundation of, well, everything we ever talk about in biology. You really get down to it.
Right. And here's the thing that really, really threw me for a loop prepping for this. I think most of us, and I'm including myself here, have this very specific mental image of DNA.
Oh, yeah.
We see it as this stone tablet, or maybe a read-only file on a hard drive that's locked away in a vault, the nucleus.
Like safe, sound, dusty.
Yeah, exactly. Just waiting to be read when the cell needs a recipe for a protein. We think of it as static.
And that is probably the single biggest misconception in all of biochemistry. We see the genome as an archive. And archives, by their very nature, are supposed to be quiet places. They're supposed to be stable.
Exactly. But the reality, according to this mountain of research on the desk today, is that the genome is actually, it's a frantic construction zone.
The very, very frantic.
It's under constant siege. It's a molecule that is practically screaming for help every second of the day.
It really is. The stability of DNA isn't a passive property. It's not like a rock. It's an active and very expensive achievement. It's a constant battle against physics.
So that's our mission today, to explore this whole concept of DNA metabolism.
I love that term.
Me too, because when I hear metabolism, I'm thinking, burning calories, digesting a sandwich. But here it means the sum of all the processes that copy our genetic code, that fix it when it breaks, and even shuffle it around.
So we're looking at replication, repair, and recombination.
The 3 R's of the genome. And we're going to need some serious guides for this because the chemistry, it gets dense fast.
Very quickly, yeah.
We do. So we are synthesizing insights from 2 absolute titans of the field today. First up, we have Lininger's Principles of Biochemistry, specifically their section on DNA metabolism.
Right.
This is our manual for the engine room, the physics, the thermodynamics, the heavy industrial machinery of the enzymes.
Lininger is just fantastic for the how. It really explains the molecular logic, the chemistry behind why things work the way they do.
And then, to keep us grounded in why this all actually matters to a human being, we've got Harper's Illustrated Biochemistry. And this acts more like our medical chart. It links all these molecular machines to the things that, frankly, scare us. Cancer, aging, genetic disease.
It's the so what. It answers that question beautifully.
Okay, so let's jump in. And I want to start with a concept that popped up in the very first pages of the Lininger notes. And I think I highlighted it like 4 times. It's just 3 words.
I think I know which ones.
Information is expensive.
Yes. Information is expensive. It sounds like something from a business textbook, right? But in biology, it's a thermodynamic law.
Can we unpack that?
Yeah.
Because my intuition was, well, DNA is just sitting there. How much can it cost to just, be?
Okay, think about writing a message in the sand on a beach. To write it, you have to expend energy. You have to move your finger, right?
Sure.
But the universe, the wind, the waves, people walking by, wants to erase that message. Entropy, the tendency toward disorder, is constantly attacking your message.
So if I want that message to stay there for 100 years?
You'd have to stand there and recarve it constantly. You'd have to fight the tide every single second. In the biological world, maintaining a specific sequence of billions of letters against all that background noise of heat and chemical chaos requires a massive constant input of energy.
So the cell is burning ATP, its energy currency, not just to build the DNA molecule in the first place.
No, not at all.
But to police it, to guard it.
Exactly. Synthesizing one chemical bond is actually pretty cheap energetically. Yeah. But ensuring it's the correct bond, that's what's expensive. The cell effectively double and triple checks its work, burning energy at every step, just to ask, are you absolutely sure that's a T and not a C?
And if it doesn't pay that energy bill?
If that tax isn't paid, the archive corrupts.
Oh.
The message in the sand gets washed away. In a cell, that means death. Or perhaps worse, it means the message changes into something dangerous. It becomes malignant. Cancer. But here's the paradox, and this is what makes this whole topic so fascinating to me. If the archive were too perfect.
What do you mean too perfect?
I mean, if the repair systems were 100% efficient and never, ever, ever let a single chain slide, evolution would stop.
Well, right. We'd still be What, single-celled organisms floating in some primordial soup because we'd never be able to mutate?
Exactly.
Yeah.
So biology has to thread this incredibly, almost impossibly thin needle. It needs enough stability to keep you alive today, right now. But just enough instability to allow the species to adapt and survive 1,000,000 years from now.
That is a wild balance to strike. Okay, so let's look at the library itself before we talk about copying it. We have to understand the terrain.
The packaging problem.
Right. Our first section here is on chromatin and the cell cycle. The scale of this is it's hard to wrap your head around. Harper's points out that if you took the DNA from a single human cell, just one, and you stretched it out end to end, it would be 2 meters long.
About 6 feet of DNA in one cell.
6 feet of thread. And that has to fit inside a nucleus that's only a few microns in diameter. That is, what is the analogy here?
It's roughly equivalent to taking a very thin fishing line that stretches from, say, London to Paris.
Wow.
And packing it inside a single golf ball.
And not just cramming it in there, right? Because if I shoved a bunch of fishing line into a golf ball, I'd never be able to find a specific inch of it again. It would be a hopeless tangle.
Yeah, exactly. You have to be able to access it. You need to read specific genes to make proteins, and then you need to copy the entire thing when the cell divides. So it has to be exquisitely organized.
So how does the cell pull that off? How does it organize a mess like that?
It uses spools. Tiny protein spools called histones. The DNA wraps around a complex of 8 of these histone proteins, what we call an octamer, and that whole unit is called a nucleosome.
This is the beads on a string picture I remember from high school biology class.
That's the one. The bead is the histone core. The string is the DNA wrapped around it about 1.7 times.
And I remember there's a clip, right? Something to keep it from unraveling.
Yes, another histone called H1. It sits on the outside of the bead, kind of like a clip, clamping the DNA where it enters and exits the spool. It stabilizes the whole structure.
Okay, so we have this incredibly tight, organized package, but Harper's makes a point that I hadn't really thought about before. This packaging, it's not just for storage, it's actually a barrier.
It's a massive obstacle. Just imagine your replication enzyme. Your job is to read and copy this text, but the text is wrapped tightly around a spool and clipped shut. You can't even get to it.
You have to, strip the room before you can paint the walls?
That's a great way to put it. Before any replication can happen, the cell has to remodel this whole landscape. It has to physically move those beads out of the way. It requires a huge amount of coordination just to expose the DNA so the machinery can touch it.
And this brings us to the timing. Because you don't want to unspool the entire library just on a whim.
Oh, no.
You only do this when you are absolutely 100% committed to dividing.
Right. And that's why replication is strictly confined to the S phase of the cell cycle. S for synthesis.
And Harper's talks about these checkpoints. It felt very, military to me. Like the cell doesn't just drift into replication. It has to get authorization.
It's a point of no return. Once a cell enters S phase, it is committed. It has to divide. It must finish the job. If it stops halfway,
that's bad.
It's catastrophic. You get a cell with, say, 1.5 genomes. That creates what's called genomic instability, which is a hallmark of pretty much all cancers.
So the rule is copy it once, copy it completely, and only do it when you're told.
And never, ever copy it twice in the same cycle.
Okay, so the command has been given. We're in S phase. The histones are moving out of the way. Now we bring in the heavy machinery. This moves us into section 2, replication. And Leninger calls this the high-fidelity copy machine.
It is a machine that operates with a level of precision that makes our best computers look a little bit glitchy.
But there are rules to the game. The first one is semi-conservative replication.
Right. This was a huge debate back in the 1950s. How does DNA copy itself?
Does it make
like a Xerox copy and keep the pristine original safe somewhere?
No. It tears the original apart.
It gently peels it apart, yes. The double helix unzips. Each strand separates. And because of those base pairing rules, A always pairs with T, C always pairs with G, each of the old strands acts as a perfect template to build a new partner strand.
So every single DNA molecule in my body right now is made of one strand that's old, maybe even from one of my parents, and one strand that is brand new, made during the last cell division.
Precisely. And that's your first layer of safety right there. You always keep the master template inside the new molecule so you can check against it.
Okay, now here's where my brain starts to cramp up a little bit. The directionality. This 5' to 3' rule. Why does biochemistry have to be so directional?
It all comes down to the chemistry of making the bond. To provide the energy for that new bond, The incoming building block, the nucleotide, brings its own fuel in the form of phosphate groups. The enzyme is designed to hook that fuel source onto the end of the growing chain, specifically the 3' end.
So the enzyme can only add new bricks to that 3' end. It can only build in one direction.
It's a one-way street, no exceptions.
Which is fine for one of the strands, right? The leading strand. The zipper on the DNA opens, and the enzyme just chases it down the line. Zoom. Easy.
Continuous synthesis. It's a smooth, easy drive down the highway.
But the other strand, the two strands are anti-parallel. They run in opposite directions. So as that zipper opens, the other strand is facing the wrong way.
And this is the famous lagging strand problem. The enzyme wants to build 5' to 3', but the DNA template is opening up in the 3' to 5' direction.
It's like trying to knit a scarf while you're walking backward away from your ball of yarn.
That's a fantastic analogy. Or imagine you're paving a road, but the paving machine only works going north to south.
Okay.
But the road is being opened up from south to north. So what do? You have to wait for a section to open up, run up to the top, pave a little section backward, then stop, run up further as more road opens, and pave another little section backward.
So it's this stutter step kind of work, and it creates these little disconnected chunks of new DNA.
Okazaki fragments, named after Reiji and Suniko Okazaki, the brilliant husband and wife team who figured this out in the 1960s.
I love that. So you have one strand being built as this nice, long, continuous ribbon, and the other strand is being stitched together from all these little pieces that have to be glued together later on.
Yes. And as you can imagine, that requires a much more complex team of enzymes to manage.
Let's talk about that team, the polymerases. Leninger focuses a lot on E. coli bacteria because they're simple, but Harper's gives us the lineup for humans.
In bacteria, it's pretty straightforward. You have DNA polymerase III, which is the main workhorse that does all the heavy lifting. Then you have DNA polymerase III, which is the cleanup crew.
Cleanup?
Yeah, it removes the little RNA primers that are needed to start each fragment, and then it fills in the gaps.
But humans, we're more high maintenance.
We are.
Yeah.
We specialize our workforce. We have a polymerase called Pol Alpha. It's the starter. It just lays down the primer to get things going, but it's not very accurate, and it falls off the DNA easily.
It just gets a ball rolling.
Exactly. Then we have a polymerase switch. Pol Epsilon takes over on the leading strand. It's built for speed and endurance, high processivity. And Pol Delta takes over on the lagging strand, handling all those Okazaki fragments.
Alpha, Epsilon, Delta. It sounds like a fraternity, but it's actually a construction crew.
A very, very precise one.
Okay, I want to visualize this machine. Leninger has this diagram that I just stared at for a solid 10 minutes. It describes DNA polymerase not as some generic blob, but as a hand.
A right hand, specifically, is one of the most powerful and useful metaphors in all of structural biology.
So walk me through the anatomy of this. I'm the enzyme. I'm gripping the DNA. What are my fingers doing?
Okay, so imagine the DNA template strand is lying flat across your palm. Your thumb essentially acts as a clamp. It wraps around the DNA and holds it tightly in place so the enzyme doesn't just fall off.
So the thumb gives it endurance, processivity.
Right. But the fingers are where the real magic happens. The fingers actually move. When a new nucleotide floats into the active site, say a thymine trying to pair with an adenine on the template, the fingers curl down over it.
Like it's making a fist.
More like a gentle squeeze to check the size and shape. It's a process we call induced fit. If the fit is perfect, if it's a perfect geometric match between A and T, the fingers close all the way. And that closing motion is what actually aligns all the atoms perfectly for the chemical reaction to happen. It positions the hammer to strike the nail.
And if it's the wrong shape, if, say, a bulky guanine tries to pair with an adenine, it would be too wide.
Much too wide. Or a CT pair would be too narrow. The geometry is clunky. It's like trying to fit a square peg in a round hole. The fingers physically cannot close properly.
And if the fingers don't close?
The chemical reaction is prevented from happening. So fidelity accuracy isn't just some abstract chemical property, it's geometry. It's the enzyme literally measuring the width of the base pair.
That's the first layer of defense, exclusion based on shape.
It is.
But, molecules wiggle, things are messy. Leninger says mistakes still slip through.
They do. Even with that geometric check, the hand still makes a mistake about once every 10,000 to 100,000 bases it adds.
Wait, 1 in 10,000. Hold on. The human genome is 3 billion letters long. If we made a mistake every 10,000 letters, we'd have, what is that? 300,000 mutations every single time a cell divided.
We would be dead. Or just a pile of tumors. That error rate is absolutely catastrophic for a complex organism. We need an error rate that's closer to 1 in a billion.
So how on earth do we get from 1 in 10,000 to 1 in a billion?
We use the delete key.
The delete key.
This is the proofreading function. Most of the main DNA polymerases have a second built-in superpower. It's called 3' to 5' exonuclease activity.
That's a mouthful.
It is. But just think of the polymerase as having two separate active sites. One is the factory floor where it builds. That's the palm. The other is, let's call it the incinerator.
The incinerator, I like it.
When the enzyme accidentally adds a wrong letter, say, the finger slipped, and it put a C opposite an A, the DNA doesn't sit right in the palm. That base pair is wobbly. It's unstable.
It's loose.
It's loose, exactly. And because it's loose, the end of that newly built strand literally frays. It flops out of the hand position and swings over into this second site, the exonuclease or incinerator site.
It gets sent to the penalty box.
And in that box, the enzyme chops off the last letter it just added. It hits backspace. Then the now clean end of the DNA swings back into the palm, and the enzyme tries again with the correct letter.
That is unbelievable. It's typing, checking its own work, backspacing, and retyping, all at incredible speed.
It happens so fast it's almost impossible to imagine. But without that proofreading, that backspace capacity, complex life as we know it, is simply impossible.
There's a thought experiment in the notes here. What happens if you genetically engineer a mouse to have a polymerase that's missing that proofreading domain?
It's a very sad experiment. The mutation rate skyrockets. The mice develop cancer almost immediately after birth. Their lifespan just collapses. It proves that life really does hang by a thread, or rather by a proofreading domain.
But even the backspace key misses things sometimes. I mean, I have typos in my emails even after I run spell check.
It does happen. Sometimes the wrong base slots in, it doesn't wobble too much, and the polymerase just zooms past it. And now the error is embedded in the new strand.
And this brings us to section 3, mismatch repair. This is the spell check that runs after the document is finished.
Right. So now we have a situation. We have a G incorrectly paired with a T. That is a mismatch. It creates a little bump, a little distortion in the double helix.
Okay, so the repair crew comes along. They see the bump. But here's the problem that I stare at for a while. We've got a G and a T. One of them is right, the original template, and one of them is wrong, the typo. But how do you know which is which?
This is the identity crisis of DNA repair.
Right. If the original template was G and you accidentally put in a T, you need to fix the T. But what if you guess wrong? What if you fix the correct G into an A to match the T?
You've just made the typo permanent. You've cemented the mutation into the genome forever. You've rewritten the history books based on a typo.
So how does the cell know which strand is the master copy and which one is the sloppy new draft?
In E. coli, we understand the mechanism perfectly, and it is just beautiful. It uses time.
Time. How?
The bacteria use a system called methylation. They put little chemical flags, methyl groups, onto specific DNA sequences. I believe it's on the adenines in GATC sequences.
Okay, so the old original DNA has these flags.
Right. The old parent strand has been around for a while, so it is fully flagged. It's fully methylated. But the brand new daughter strand hasn't been flagged yet. The methylating enzyme is a bit slow. It takes a few minutes to catch up to the replication fork.
So there's this little window of opportunity.
A critical window. For a brief period right after replication, the two strands look different. The old one has flags, the new one is naked.
So the repair enzymes, these proteins called MUTs and MUTL, they scan the DNA, they find the bump from the mismatch, then they look for the flags, and they know, okay, the one without the flags is the new guy. That must be where the error is.
And they specifically chew up a segment of the unmethylated strand, remove the error, and a polymerase fills it in again correctly.
It's genius. It uses a temporal delay to distinguish old from new and ensure fidelity. But what about us? Harper says humans don't use that same GATC methylation trick.
We don't. And for a long time, this was a huge mystery. How do human cells distinguish the strands?
Do we know yet?
The leading theory is that the cell uses the necks, the little breaks between those Okazaki fragments on the lagging strand, as the signal for newness. The new strand is the one that isn't one continuous sealed piece yet.
That makes a lot of sense. The broken one is the new one.
But however we do it, we know just how vital it is. Because when the system breaks, the results are devastating. And this is where we have to talk about Lynch syndrome.
Also known as HNPCC.
Right. Hereditary non-polyposis colorectal cancer. It's a genetic condition where people inherit a broken copy of one of these mismatched repair genes, the human versions of MUT-TES or MUT-TL.
So their post-replication spell checker is basically offline?
Partially offline, yes. And the result is that mutations accumulate at a terrifyingly rapid rate. For reasons we don't fully understand, the cells lining the colon are particularly sensitive to this. These patients have a massive, massive risk of developing colon cancer, often in their 30s or 40s.
Wow, it really drives home the point. These enzymes aren't just abstract bubbles in a textbook diagram. They're the only thing standing between us and cancer.
Absolutely. Mismatch repair boosts the accuracy of DNA synthesis by another factor of 100 to 1,000.
Yeah.
It is the difference between a functional genome and a completely chaotic one.
But here's the really scary part, and this is section 4 of our outline. We've been talking about errors that happen during copying, typographical errors. But Leninger makes it very clear that even if we never copied our DNA again, even if a cell just sat there doing nothing, the DNA would still be falling apart.
Yes. This is DNA repair, fixing a broken world.
I think we had this idea that DNA is super stable because, we find it in dinosaur bones. But chemically, in the warm, wet environment of a cell, it's actually fragile.
It's surprisingly fragile. It is under constant, relentless bombardment from its own environment.
Who are the enemies here?
Well, water is the first one.
Water. But we're mostly water.
Exactly. And that water is constantly attacking the chemical bonds in DNA. We lose thousands of purine bases, the adenines and guanines from our genome, every single day in every cell, just due to spontaneous hydrolysis. The bond just snaps, the base floats away, and you're left with a blank spot.
That is deeply disturbing. My DNA is losing letters just by being wet.
Then there's deamination. This is a huge one. The base cytosine, the letter C, is chemically a bit unstable. It has a tendency to spontaneously lose an amino group, and when it does that, it turns into uracil.
Uracil. But uracil is an RNA base. It doesn't belong in DNA.
It absolutely does not. And here's the danger. C is supposed to pair with G, but uracil pairs with A.
Oh, I see the trap. So if a C turns into a U, and the cell doesn't notice and fix it, the next time you copy the DNA, the polymerase sees a U, puts in an A, and suddenly a CG base pair has permanently become a TA pair. You've mutated the code.
That's right. The deamination of cytosine is one of the most common sources of spontaneous mutation in our cells.
So how do we fix it? We need a system that can patrol the DNA, spot a U, and say, hey, you don't belong here.
And we have one. It's called base excision repair, or BER. I like to call this one the scalpel.
The scalpel.
It's incredibly precise. It's for these small, non-distorting lesions, like finding a single broken tile in a huge mosaic floor. The key enzymes are called DNA glycosylases. These enzymes just patrol the DNA double helix, constantly scanning, and they're highly spiralized. For instance, uracil DNA glycosylase only looks for uracil. It ignores everything else.
You know what happens when it finds one?
This is one of my favorite mechanisms in all of biology. The enzyme literally grabs the bad base and flips it completely out of the stack.
Wait, it flips it out of the helix?
The base is normally tucked away neatly inside the helix. The enzyme forces it to swing out 180 degrees, so it's just sticking out into space like a loose thread on a sweater. Then, snip. It cuts the bond holding that base to the sugar backbone.
So it removed the letter but leaves the paper it was written on.
Perfectly put. It creates what's called an abasic site, a hole where a letter used to be. Then a different set of enzymes comes in, AP endonuclease to cut the backbone, a polymerase fills in the correct C, and an enzyme called ligase seals it all up.
It's surgical. Flip, snip, patch, seal.
But what if the damage is bigger? What if it's not just a single changed letter, but a major structural disaster?
Like what, for example?
Like damage from ultraviolet light, sunlight.
Yeah, right. The sun, we all know UV causes skin cancer. But what is it actually doing to the DNA molecule?
It causes something called pyrimidine dimers. If you have two thymine bases sitting next to each other on the same strand, the energy from a UV photon can cause them to form a covalent bond with each other. They get fused together.
Like melting two plastic Lego bricks together so they're permanently stuck.
Yes. And this creates a big, bulky kink in the DNA helix. It severely distorts the shape. The replication machine, the polymerase, cannot get past this damage. It just stalls. This isn't a single broken tile anymore. This is a giant tree root growing up through the sidewalk. The whole slab is buckled.
So the scalpel, the glycosylase, that's not going to work here. The damage is too big.
Nope. For this, you need the sledgehammer. Or, maybe more accurately, the circular saw. This is nucleotide excision repair, or NER.
NER. How is it different from the scalpel?
Instead of picking out one single bad base, a massive protein complex scans the DNA, looking for these bulky helix-distorting bumps. When it finds one, it doesn't just cut out the two fused bases. It makes two cuts in the DNA backbone, one on each side of the damage.
Cuts out a whole section.
A huge chunk. In bacteria, it's about 12 or 13 letters long. In humans, it's around 29 nucleotides. It just peels that whole single-stranded segment away, leaving a massive gap.
It's like replacing an entire plank of a wood floor instead of just trying to sand out a scratch.
Exactly. Then polymerase comes in, repaves that whole section, using the other strand as a perfect guide, and ligase seals the ends.
And we know this is absolutely critical because of what happens when it's missing. Harper's discusses the disease xeroderma pigmentosum.
XP. It's a rare and really heartbreaking genetic disease. These individuals, they're often called the children of the night, have a genetic defect in their NER pathway. They're missing the SAW.
So they can't repair UV damage.
They cannot. If they step out into the sun, the UV damage happens, the thymine dimers form, but their cells have no way to fix them. The kinks just stay in the DNA. They accumulate.
And the replication machinery hits those kinks and just makes mistakes.
Massive amounts of mistakes. These patients develop hundreds, even thousands, of skin cancers, basal cell, squamous cell, melanoma, often starting in early childhood. It proves a really chilling point. The only reason you and I can walk to the grocery store in the daylight without getting cancer is that our NER system is frantically sawing out sun damage every single second we are outside.
We are constantly healing from just being in the sun.
Constantly. It's a war of attrition.
Before we move on to the really big disasters, Leninger mentions one other repair mechanism that I just found really, poetic, the suicide enzyme.
Ah, yes. O6-methylguanine DNA methyltransferase, or MGMT for short.
A slightly catchier name, but the mechanism is just wild.
It's a form of direct repair. Sometimes a chemical agent will attach a methyl group to a guanine base where it shouldn't be, and this messes up the base pairing.
And most repair systems would cut it out, right? Like with BER.
They would, but this enzyme is different. It doesn't cut the DNA at all. It reaches into the helix, it grabs that rogue methyl group, the poison, and it transfers it directly onto one of its own amino acids.
It takes the poison pill itself.
It does. It chemically damages itself to fix the DNA. But here's the catch. Once the enzyme takes that methyl group, it's permanently inactivated, it's dead, it can only work once, and then it's garbage.
That seems incredibly wasteful. I mean, proteins cost a lot of energy to make. Why would the cell sacrifice an entire massive protein just to fix one tiny methyl group on one letter of DNA?
Because, as we said at the very beginning, information is expensive. The DNA is the master blueprint. The protein is just a worker, a copy made from the blueprint. The logic of the cell dictates that it is worth sacrificing 1,000 workers to ensure the blueprint remains absolutely pristine.
The protein literally falls on the grenade to save the code.
It just shows you the hierarchy of value inside the cell. DNA is king. Everything else is expendable in its defense.
Okay, so we've fixed the typos, we've fixed the kinks, but now we have to face the nuclear emergency. Section 5, the double-strand break.
This is the worst-case scenario for a chromosome. A double-strand break, or DSB, means the chromosome has literally been snapped in half. Both rails of the train track are severed.
The cable has been cut.
Right. And if you don't fix this, that piece of chromosome can just float away. You lose hundreds or thousands of genes. Or, even worse, the broken sticky end attaches to a different chromosome where it doesn't belong.
Which is a translocation. That's a cause of some leukemias, right?
It causes all sorts of cellular havoc. The cell has to fix this, and it has to fix it immediately. This is a code red emergency.
And there are basically two ways to handle it. One is fast and dirty, and the other is slow and perfect.
That's a great way to put it. Pathway 1 is non-homologous engyning, or NHEJ.
I call this the duct tape solution.
That is a very fair description. The cell essentially sees two broken ends of a chromosome flailing around. It grabs them with a pair of proteins called Q70 and Q80.
The Q protein.
They act like a clamp, holding the two ends close together. Then other enzymes come in. They trim the ragged edges to make them flat, and a ligase just smashes them back together.
But wait, if you trim the edges, aren't you losing information, losing base pairs?
You are. You almost always lose a few nucleotides at the junction. It leaves a small deletion, a scar.
So why do it? Why would the cell ever choose a repair method that intentionally deletes information?
Because a small scar is infinitely better than a completely broken chromosome. It's triage. The cell accepts a small, localized error to prevent a massive, catastrophic one. This is the pathway the cell uses when it has no other choice, usually in the G1 phase of the cell cycle before the DNA has been copied. You don't have a backup copy to look at.
Yeah.
So you just have to stick it back together and pray the few letters you lost weren't vital.
But if you're in the S phase or the G2 phase, you do have a backup.
Exactly. After replication, you have an identical copy right next door. And that unlocks pathway 2, homologous recombination, or HR.
The perfect solution.
This one is just beautiful. Since you've replicated your DNA, you have a sister chromatid right there next to the broken one. The sister is an identical clone.
So you can use it as a cheat sheet.
A perfect cheat sheet. The cell detects the break, but instead of smashing the ends together, it does something amazing. An enzyme chews back the ends of the break to create long, single-stranded overhangs. One of these strands then literally reaches out and invades the healthy, intact sister chromatid.
It invades its neighbor.
It pushes its way into the neighboring double helix. It scans along until it finds the matching sequence. When it finds the right paragraph, it uses that healthy sister strand as a template to perfectly copy the information that was lost in the break.
It rewrites the lost data by reading from the backup drive.
And then it brings that newly synthesized correct strand back to its original chromosome to bridge the gap.
So no information is lost at all. It's a perfect restoration.
Perfectly. It's a high-fidelity, flawless recovery.
And this brings us right to the Angelina Jolie effect. We hear about the BRCA genes all the time in the news. BRCA1, BRCA2.
They're household names now, which is incredible. But most people don't know what they actually do inside the cell.
And Harper's explains it. They are part of this specific repair team, right? The HR team.
Yes. BRCA1 and BRCA2 are essential scaffold proteins for homologous recombination. They are the managers of the repair site. They help organize that invasion step where the broken strand seeks out the template.
So if you inherit a mutated, broken copy of BRCA1,
you lose the ability to do the perfect fix. When your DNA suffers a double-strand break, and this happens all the time from normal metabolic stress, your cells are forced to rely on the duct tape solution, NHEJ, or other even messier pathways.
And the scars, the deletions, they start to accumulate?
The scars accumulate. The genome becomes unstable. Large chunks of chromosomes get rearranged or lost. And in tissues that are driven by hormones to divide, a lot like breast and ovarian tissue, this genomic chaos eventually leads to cancer.
It's just amazing to connect a molecule like BRCA1, which for many people is just a scary medical test result, to a specific mechanical job in the nucleus. It's not magic. It's just a broken tool in the repair kit.
It completely demystifies the disease. It helps us understand exactly why that risk exists.
All right, we're heading into the home stretch here. Section 6. The so what. We've touched on cancer a few times, but let's really solidify that link.
To do that, we have to talk about the Ames test. Leninger has a great little sidebar on the history of this.
This was the test that really proved the connection, right?
Right. Bruce Ames, back in the 1970s, he asked a very simple question. Are carcinogens, things we know cause cancer, also mutagens, things that damage DNA?
It seems obvious to us now, like, duh, but back then we didn't actually know.
We didn't. Some people thought cancer might be caused by viruses or was a purely metabolic disease. Ames developed this very simple, elegant bacterial test to see if chemicals cause mutations. And the answer was a resounding yes. Something like 90% of known carcinogens are also potent mutagens.
So the equation is simple. Damage to DNA leads to mutation, which can lead to cancer.
It's a direct causal line.
And standing in the way of that line is a protein that Harper's focuses on heavily. They call it the guardian of the genome, P53.
P53, or TP53, the gene. It is probably the most famous protein in all of oncology.
What makes it the guardian?
P53 is both the sensor and the decision maker. When DNA damage happens, when the helix is cut or kinked or mismatched, alarm bells start ringing in the nucleus. Kinases, enzymes like ATM and ATR, get activated by the damage, and their job is to wake up P53.
And once it's awake, what does P53 do?
It assesses the situation. It's like a foreman at a construction site that's had an accident. If the damage is fixable, P53 halts the cell cycle. It puts up a big stop sign at the G1S checkpoint. It basically says, nobody divides until the repair crew fixes this mess.
So it buys time. It gives the enzymes we just talked about, the NER machinery, the HR machinery, time to do their work.
Exactly. It prevents the cell from stupidly copying damaged DNA, which would make the problem permanent.
But what if the damage is too bad? What if the radiation dose was too high and the chromosomes are shattered?
Then P53 makes the hard call. It triggers apoptosis.
Programmed cell death, cellular suicide.
It orders the cell to commit suicide. It activates a whole cascade of enzymes that go and chop up the cell's own DNA and dismantle the cell from the inside out safely.
It sacrifices the one damaged cell to save the entire organism.
Better to lose one cell than to let it become the seed of a tumor.
So what happens in cancer? Because clearly cancer cells are full of damage, but they don't die.
Because in over 50%, some sources say up to 80% of all human cancers, the p53 gene itself is mutated and broken. The guardian is offline.
So the damage happens, the alarm bells ring, but nobody answers the phone?
The cell just plows right through the checkpoint, dividing with broken DNA. It accumulates more mutations, it becomes more aggressive. The loss of p53 is very often the tipping point, where a precancerous growth becomes a full-blown malignancy.
Man, it really puts into perspective how fragile and yet how incredibly resilient we are. We have these layers upon layers of defense.
The geometry of the polymerase hand, the proofreading delete key, the mismatched spell checker, the excision repair saws, and then finally, p53 standing there, holding the kill switch.
It's a fortress with multiple walls.
So let's bring this all home. We've gone from the nanoscopic geometry of the double helix all the way to the oncology ward. We started with this idea of a dynamic archive.
I hope that image has completely replaced the stone tablet in everyone's mind by now. The genome is not a document in a vault. It is a document that is being frantically retyped, spell-checked, taped back together, and guarded every single second of your life.
And a cost back to information is expensive.
It's the ultimate energetic argument. Biology is willing to burn its most precious currency, ATP, at an alarming rate just to maintain the sequence. It is willing to sacrifice enzymes like MGMT. It is willing to kill its own cells via p53, all to protect the message.
Because without the message, there's no future.
There's nothing.
But I want to leave our listeners with that final provocative thought that you teased at the very beginning, this idea of balance. Yes, it's the philosophical capstone to all of this dense biochemistry. We have these incredible multi-layered repair systems. They are amazing, but they are not perfect.
And if they were perfect?
If DNA repair were 100% perfect, if no error ever slipped through, if every single base was preserved with absolute fidelity from the beginning of time, you and I would not be here.
There would be no variation, no raw material for natural selection to act on.
Exactly. We exist because our repair systems are brilliant, but they are also just imperfect enough to allow for change. We are the product of the errors that slipped through the cracks. We are the descendants of the mutations that turned out to be features, not bugs.
That's a beautiful way to put it. We are the survivors of the failed repair jobs that just happen to turn out to be improvements.
In a way, yes. Our flaws are, quite literally, our future.
I love that. Our flaws are our future. Well, if you want to see the diagrams of these incredible molecular machines, and trust me, the hand of the polymerase and the clamp of the MUT proteins are absolutely worth seeing. Open up Leninger or Harper's. It's like looking at the blueprints for a spaceship.
Highly recommended.
Yeah.
It really makes the abstract real.
Thanks for listening to this deep dive. We'll see you next time.
Stay curious.